Good afternoon. Welcome to this session in the short course on laser remote sensing. Today we will be talking about a type of laser scanner which is placed on the ground. It is a ground-based terrestrial laser scanning system, and the instrument is called a terrestrial laser scanner. So you are already aware from yesterday's lecture that to do 3D data collection, or that is to collect the Z coordinate, information about the Z coordinate along with the X and Y, we can have either image-based techniques or range-based techniques. Along with this, we also have manual methods like surveying methods, where we can use plane table surveying, total station, GPS, etc. Image-based techniques are basically photogrammetry based. So there also we can have satellite, aerial, and terrestrial platforms. These techniques give us dense and sparse point clouds. The range-based techniques, as the name suggests, are for range-based techniques in optical scanners are the laser sensors. These can be aerial, terrestrial, or spaceborne, and these give us very dense, high resolution 3D point cloud data. These are very quick. We can acquire this data very fast, and it is easy to use, but expensive and computationally very comprehensive to process. So keeping in mind all of these, the range-based 3D modeling techniques can be either discrete data or full waveform format data. They give us very high vertical accuracy. So measurements in the Z coordinate are very, very accurately measured. Very high precision is there. The method is easy to use. Some sensors give us discrete data, and there are also sensors which give us full waveform data. In the next sessions, you will be discussing about how full waveform data is acquired and how it is different from discrete data, and what are the advantages of using the full waveform data from the laser sensors. Now, just to give you an idea or define full waveform data, the full waveform type of sensors sample the return signal very rapidly, and then they store the entire backscattered energy of the emitted pulse. So the entire signal which is returning is measured, unlike discrete, the sensors which are based on discrete measurements, where single returns or discrete returns are measured. And with the full waveform data, we can also have, along with the range, we can get some other physical properties of the backscattered echo, like width or amplitude, etc. This enables us to do better identification of objects like buildings and trees, etc., even when we are using a large full waveform sparse data like the satellite data or Lidar or the discrete aerial Lidar. Then if we compare this with terrestrial photogrammetry, this technique gives us very rapid image acquisition, low cost of acquisition, because we can use any type of camera, even the ones which are on our mobile phones. These also give you very high accuracy. They are portable and flexible, and the 3D modeling of engineering structures, buildings, trees, etc., other features on the surface of the earth can be done. However, we will be focusing our discussion on the range-based method of 3D modeling, and the sensor is placed on a terrestrial platform. So laser sensors, as we have been talking about, can be either ground-based sensors, like the one we are going to be discussing in detail in today's discussion, the terrestrial laser scanner. This is the terrestrial laser sensor. This is mounted on a tripod, and it can be static, like this, mounted on a tripod, and then measurements are taken and then moved to the next location to cover the entire structure. or it can also be mobile. So we can put it on a mobile platform like a vehicle and move the vehicle along the corridor like a road corridor, etc., and do mapping. Uh, Lidar sensors can also be mounted on airborne systems, which can be manned like an aircraft or unmanned like drones, etc. UAVs, unmanned aerial vehicles. Then the third type of platforms are spaceborne platforms, that is satellite-based platforms. And these are few examples of Lidar sensors on spaceborne platforms. This will be discussed in the next section. Now, when we talk about terrestrial laser scanner or a laser scanner which is placed or mounted on a ground-based platform, we call it terrestrial lidar or a tripod lidar. It is a ground-based remote sensing tool which is similar in its measurement method to the radar or the sonar, but this uses a visible to near infrared light which is emitted from a laser instrument, and then it records the reflected light waves from its target. So these recorded light waves can then be converted into coordinates with x, y, and z, into points with x, y, and z coordinates, and this can be georeferenced with a GPS unit to produce very, very precise, accurate three-dimensional data sets called point clouds, and these can then be analyzed for scientific research. Now, terrestrial laser scanner, or TLS as for short, is a tool that is becoming very, very popular in the field of earth sciences or mapping applications. We can use it for topographic mapping, change detection due to phenomena such as earthquake, volcano, landslide, morphology, river morphology or stream morphology studies, changes in the glaciers, and things like snow depth measurement, etc. All these can be done with very high precision and accuracy, if very high accuracy requirements are there. Because it gives us data at a very high resolution, very dense data. The sampling interval is very, very fine. The TLS is also very widely used in documentation of built heritage sites, architecture, biomass investigations in forestry, etc., and for numerous other engineering applications. Now, the kinds of laser scanners can be divided into three different types. They can be either a camera-based scanner, a panorama scanner, or it can be a hybrid scanner. So the camera scanner has a limited field of view. For example, it could be about 40 by 40 degrees. It is comparable to, we can say, a photographic camera. This type of scanner is optimized for view from, taking from outside and taking the object. Normally, a long distance range measurement device is used. So we place it outside the object, and then the laser waves laser wave is sent, beam is sent, and the reflected, the backscattered or reflected beam is sensed or recorded by the receiver. Then the panorama type of scanner, the field of view is only limited by the base of the scanner. So it has a larger field of view, which this base of instrument includes the tripod. So this type is designed for indoor purposes. For example, if we have to do data collection for interiors of rooms or buildings, etc., or any other facility. Then we also have hybrid kind of scanner. This is a mixture, as the name suggests, it is hybrid. So one rotation axis is without restriction. So this is often mostly the horizontal movement. And the second axis of rotation is due to the use of mirrors. And so 100 degrees in the vertical and 360 degrees in the horizontal. So this is a mixture of both, and it can be, the movement can be in both. And with use of mirrors, the second rotation axis is operated, and we can do horizontal and vertical scanning. We can also select AOIs, and only those particular AOIs or area of interest can also be scanned using the hybrid scanner. Now, what are the kinds of objects or applications we can do when we are choosing static laser scanning, and in which cases we can do dynamic laser scanning? So for mobile mapping or road tracks, etc., when we can move across the corridor and do the scanning. Static laser scanning can be close range, that is the object and the sensor distance is less. It can be medium range, and it can be long range or very long range. So if the object is at a distance, or it is a very large object like a landslide, etc., or a glacier, or maybe sometimes for forestry related studies, we can use a long range scanner. If we need to do some very precise and small objects, then we can use close range scanners. For other applications, medium ranges would do. So for long range scanners, for example, if we have to do some monitoring changes, like I said, landslides, glaciers, etc., mining related applications, right, or city modeling. Medium range scanners can be done for civil engineering applications, architecture, cultural heritage, facility management, etc., or industrial uses. Close range, as I said, if it is to be for medical purposes, or a small object has to be done, scanned and measured. So this will be done at a very high resolution. Now, major features of terrestrial laser scanners are that they have a variable range, as you can see, right? They can range from few meters, few hundred meters to few thousand meters. Right? It has a wide field of view, which is controllable while scanning. So we can choose the area of field of view, how much we want to scan, depending upon the type of object and the type of data that is required. High accuracy, high precision ranging is based on the echo digitization and online waveform processing. It has integrated inclination for sensors, laser plummet and compass, and an integrated GPS receiver. So now if you see here, this is the laser sensor, scanner and rotating mirror to facilitate scanning in the vertical and horizontal axes. This is the camera, RGB camera, which also clicks images at the same time that the scanning is happening. And this is the GPS receiver with the antenna. So here what is happening, by ranging we mean that we are measuring georeferenced point clouds, which are produced by measuring the distance between the scanner and the target. Now, this occurs just as the laser sensor emits short pulses. These are point sources of light that are reflected back and recorded by the receiver. The distance is then calculated by multiplying the round trip travel time of time of flight of the initial pulse and the return pulse by the speed of light, and then dividing it in half. So range can be calculated by travel time multiplied by speed of light and dividing this by 2. Now it records, along with the range, it also records azimuth, zenith, and the intensity. So the transmitter sends the pulse, it strikes the surface and comes back to the receiver. And then we calculate the distance. And this is converted into, we take the Z coordinate measurements with the help of this. So once the pulses are sent, you can see they are very dense pulses, and these kind of points, each point is associated with X, Y, and Z coordinates. So the entire region inside a definable window is scanned very quickly to the tune of minutes or seconds, and we get accuracy in millimeters or centimeters. Now we will talk about how to set the scanner parameters for different kinds of data collection. So the scanner parameters are basically beam divergence, the ones that the users can change according to their requirement to get optimum kind of data, which will enable you to do measurements in 3 dimensions. So we can manipulate the beam divergence, the angular step, the range distance, field of view, how many points per second are to be collected, and of course the size and weight of the scanner. So beam divergence is very, very important consideration in the terrestrial laser scanning. Here the laser beam is a cylindrical beam of photons, as we have seen here. So it is a beam of photons that slightly deviate when it is first emitted from the laser. Now, as it travels from the laser, from the terrestrial scanner, the beam begins to widen. As you see, it begins to widen, right? As the narrow cone that increases in diameter, and the further it travels, therefore it is called the beam divergence. So here you see the oval, orange oval here represents the beam spot size, and the blue lines represent the it's a hypothetical rock outcrop or a surface. So beam divergence as distance diverges as the distance increases from the laser. So for different instruments, there are different beam divergences. So the diameter can be calculated by the spot diameter can be calculated by using beam at exit plus divergence, which is in radians, into distance. So with this, if we have these parameters of the scanner, then we can calculate the diameter of the beam, how much divergence. Now diameter at exit ranges from few millimeters to some centimeters. Now here you can see in the top and bottom figure, the laser at both scenarios is hitting the same target, traveling the same distance, but in the top figure, this laser has smaller beam divergence, and this results in smaller spot size, right? Smaller beam divergence, you can say smaller spot size. This allows, the spot size is smaller. It means that we will have increased or finer resolution and better detailed images. So more irregular, if it is an irregular surface, we will be able to measure those irregularities in a finer resolution. Now here in the bottom figure, it produces a lower resolution, less details, and average image. So because the beam divergence is more, the spot size has increased. Now spot size on target will be function of the diameter of the initial beam as it exits the laser, the beam divergence, and the distance it has to travel until it hits the target. So we can see this here with this relationship. Okay. Now this corresponds to beam widening approximately 3 centimeters per 100 meters. And the resolution of the scan will be affected by this parameter as the final spot size of the beam that intercepts its target illuminates the certain area. Now the attributes within the spot will be averaged and recorded by the receiver. Therefore, we can conclude that wider the spot size diameter, the less overall detail we will gain on a scale which is smaller than the spot size. Now, how the second one is spot spacing. The scan parameter which will affect the resolution before we start scanning is spot spacing, that is angular resolution. What will be the angular resolution of the scanner? What should we set it at? So this is a function of the stepping angle, and stepping angle means increments for each set of pulse of the laser and range to the target. Spot spacing can be reduced or increased by adjusting the stepping angle or angular step in the scanning software. So these are all the settings that we have to decide and do before we start scanning. We will set these, do the scanner setup, and fix these parameters. Now this will result in increasing or reducing the resolution respectively and the corresponding density of points or the data collected by the spots or points collected by the scanner. Increasing distance increases the spot spacing. So angular step will be needed to be reduced to obtain a higher resolution scan at long ranges. So if the object to be scanned is at a distance that is at a long range, then we will have to reduce the angular step to obtain a high resolution point cloud. Now, angular step can be adjusted for both vertical and horizontal scanning ranges. Then, if the area is large, we will have to partition the area into different regions and then do the scans. So we may have to partition it into 2, 3, 4 areas. So for large topographic scans, it will have varying ranges within the target scan, and this can affect the point density and the resolution. Now, if the same resolution and point density is desired over wide range of distances at one scan location, for example, if it is a river channel and adjacent terraces on a slope, etc., hill slope, then the scan will have to be broken up or partitioned into several scans at determined mean distance intervals. Then the stepping angle we will need to adjust the stepping angle as a function of the mean distance to achieve the same resolution and the point density. If we do not do this, then the extreme scans, for example here, R1 and R3, will either be too dense or too sparse. So since the terrestrial laser scans in terrestrial laser scanner scans in the vertical and horizontal orientations, vertical and horizontal partitioning needs to be taken into consideration when we are doing scanning for a complex project. Now, you should note here that beam divergence will also play a role in the desired resolution, and it will determine the location of the scan positions also. So, for example, if we look at this, we have partitioned this into three areas, R1, R2, and R3. Now, if the same stepping angle was used for R3 that was used for R1, then we can comprehend that the spot density for R1 could be about 10 to 15 times that of R3. This will require more time to scan, and it will also take up more memory on your computer system. Then along with these settings, we also have range distance. This means that the target reflectance can change single scan ranges by hundreds of meters laser and CCD characteristics. This will impact minimum and maximum range distance from 300 to 6,000 meters. Then field of view, rotational base. So as I said, field of view, it can be 360 degrees and can also be in the vertical. Then how many points per second do we scan? This will determine your scan time. And field logistics like the size and weight of the scanner will of course be some important. Now, how do we set up and what is the workflow? So the scanner setup. The first thing is, where do we place the scanner? So the scan positions have to be selected very discreetly. The first step is to select effective scan positions that will maximize overall coverage and maximum coverage of the target site to minimize occluded views that will lead to blank spots in the point data. Now here a good practice is to pick at least 2 oblique locations like we've seen here, but sometimes you can also have a third scan so that anything that is missing can be included. And we also have strong angles of incidence with the target. Now, if we want a true 3D model, then we must move the scanner around the structure to get the scans. So multiple scan positions need to be are needed to obtain maximum coverage of the feature through overlapping illumination of the target like this. So we move all around the object and take multiple scans from multiple positions. This will minimize the amount of the unilluminated area and therefore reduce unmeasured features. Therefore, in cases like this where we are taking two oblique scans, a scan in the middle would be helpful. It may sometimes not be that necessary. So we have to decide as per the study site how the scan positions are to be located. Whether you need two scan positions or you need a third scan position to maximize the data collection, optimize the data collection. And wherever needed, we can also do multiple scans, all covering the 360 degrees of the object. Then we have to, once we decide the scanner setup, we need to decide where the control targets or tie points are to be set up. So these are the targets. These are an example of the target. So these are produced at set locations in the study site so that they can be used to stitch the multiple scans together, and they are used as tie points like we know from photogrammetry. So control targets are essential to register multiple scans as they are static markers that allow for easy merging of multiple scans that we need to produce a three-dimensional data set. Now, the control targets should not be placed in a linear fashion or they should not be bunched up together, but they should be evenly dispersed around the entire scan site as much as possible, both horizontally and vertically. Something like how we place the or measure the GCPs in the image. Now, minimum of 3 control targets should be deployed, but it is highly recommended to have at least 5 so that we account for controllable sightline blockages in areas where there is complex topography or maybe dense vegetation, etc. Or say in case of architectural monuments, if they have very complex structure, more curves and many other complicated design, etc. So the more targets in common between the adjacent scan, the better the accuracy of the final point cloud product. Okay? So the targets should not move during scanning. So a secure placement, we should ensure that the targets are securely placed. Usually they have staffs on which they can be mounted, or they have tripods on which you can mount these and then secure them at the location. So that position should be fixed and there should not be movement of the control target, because movement will introduce error and this will possibly, sometimes it can be severe or to such an extent that we might have to restart the scanning. So here we have examples of how the target geometries can be represented. So this is a good target geometry. This is a bad target geometry, and this is not at all recommended. Right? So these are vectors radiating from the scanner to the target. Now, here this is an example where the yellow stars represent the target control targets. So this is the entire area to be scanned, and the colored circles give the scan positions here. 1, 2, 3, 4, 5, and 6. So from 6 target location, 6 scan positions, the scanning was done to cover this area, and the target control points were placed at these yellow markings. So here, if you notice, each scan position contains several target points in common with each other, so that they can allow for proper registration of the multiple scans. So the same target point will occur in multiple scans, in this, in this, in this, like this. Similarly for others. Then how to do the GPS setup for the study area. If georeferencing of the scans is required for the project, then the two most common GPS techniques that we can use in the terrestrial laser scanning project are the static, where we do a long occupation, and RTK, or real-time kinematic GPS. So which one we have to use depends on the specific needs of the project and the equipment availability. So both forms of differential GPS require a base station within range and clear sky for accurate and precise measurement. For the static GPS, it is very accurate. It requires at least 3 antenna receivers, which are configured in a triangular geometry on top of specific control targets within the project location. Now, long occupations up to 6 to 8 hours are required here to obtain optimal position solution, which will give us centimeter to sub-centimeter resolution accuracy. So the longer the epoch is, the better it will be. The base station, which is placed on site, or we can use an established base station, which is at a distance with known coordinates, is also required to post-process and differentially correct the GPS data. This can be done later on in the lab. Now, for the RTK GPS, which is a real-time kinematic GPS, this is also useful because it is quick and it provides real-time position solutions. Therefore, it requires less equipment and it's easy to carry in the field. It involves a base station setup on the site at the beginning of the project, and this collects data throughout the day. The base then provides real-time correction data via radio link to a receiver called the rover unit. Therefore, occupation time can be within seconds to minutes and no need for post-processing like in the static GPS. So position solutions are in centimeter scale, averaging between say 2 to 5 centimeters. Now, a disadvantage or a limitation for RTK versus static type of GPS setup is that the need for clear sight for the radio communication between the base station and the rover. This can sometimes be, if we have a large site to cover, it can sometimes be limited by complex topography or dense vegetation. Then other parameters like beam divergence, spot spacing, scan partitioning are already done before the beginning of the scan. Now, we also have to be aware of the angle of incidence. This is related to the angle of the beam that intersects the target. So we have to ensure that we have strong angles, that is maximum coverage and overlap between scans is ensured. Then environmental conditions will also be a factor, such as position of the sun related to the scanner and so on. So albedo, that is the reflectance of the scanned material, if it is very highly reflecting like marble, etc. Visibility limitations due to clouds, dust, topographic relief, etc. and vegetation can sometimes also affect the quality of the reflected or returned data. Now, when we are collecting data, after the control and GPS framework has been established to coincide with predetermined scan positions and data collection, then we can begin the data collection. So we start with a panorama scan of the area accompanied by digital photos. So the photos are simultaneously clicked by the scanner. Next, a fine scan can be done of all the control targets as part of the scan registry process. Now, once this is complete, a fine scan of an area of interest, that is the focus of the project if we require. So we can decide to scan different areas of the project study area in different ways. So if in particular locations, if the focus is to get very high or very dense, ultra high resolution 3D point clouds, then a fine scan can be done. Otherwise, medium density scans can be done for the entire study area and so on. Now, after the first scan is complete, we then move to the next scan position. For each successive scan position, we repeat the basic steps that we have discussed and then register or tie together the adjacent scans by finding or locating the corresponding points in which the control targets help us. Then we check the accuracies of the scan registration in the field itself so that there are no unpleasant surprises when we come back to the lab. So that if we require to recollect some data, we can do that while we are still in the field. Then GPS data can be imported into the scan and while we are after we have scanned, and we should make sure that we have saved all the data. Then another concept that we need to make ourselves familiar with is that there are certain coordinate systems that we need to be aware of. So when using a terrestrial laser scanner, the scanner can be tied to any one of the 3 coordinate systems. So the first system is the scanner's own coordinate systems, and it is usually called SOCS, SOCS. The first set of coordinates that it establishes for the individual scan related to the scanner's position. Right? So this is called the SOCS, scanner's own coordinate system. Then the project coordinate system, when we have multiple scans registered together using stationary control or try points, which are dispersed around the project area. And the third type is the global coordinate system. So independent GPS coordinates are then imported and registered into the point cloud to create a georeferenced final product. So the 4 scan coordinates here in this figure you can see SOP 1 to 4, 1, 2, 3, and 4. Right? So this involves the scanning of an object here, and then they are registered together to create a overall project coordinate shown in the red axis. And then after the GPS data has been integrated, then the point cloud is now georeferenced in the global coordinate system, these black axes. So co-registration of stitching of data is very important. So this is how the scanner own coordinate system is calculated based on the position of the scanner. So at a scan position, one particular scan position, all positions are located with respect to the SOCS, which is inside the laser scanner. Now we can also combine other kinds of data with the laser scanner data, for example, photographs, to enhance the color information that we have. Because the terrestrial laser scanners already have a calibrated camera with them, RGB images can be taken. So these can be very useful for damage assessment or other kinds of measurement, as these will give us enhanced color information for the object also, along with the point cloud data. So while we are doing, so the basic steps for the project planning now, once we have collected data that we can look at. So when we do the project planning, we have seen how to set up the scanner location, then where to place the targets, what are the field constraints and logistics that we have available. So the data collection, that is the laser scan, the GPS, the photographs, etc. Then these have to be registered and georeferenced. Registration of the scans from a single scan campaign or a single data collection campaign or a project. So multiple scans with the help of the control targets have to be registered together, and then editing and cleaning of the point cloud data is done, refinement. Then the point cloud data can be reformatted, and if it has to be interpolated to create a kind of DEM, etc., we can do that. Then we can also integrate the 3D point cloud with other data sets, say GPR, or we can use this as an input into GIS and so on. 3D models can be created for photorealistic modeling. Surface modeling can be done, DEMs, etc., for large surfaces. And then combining the data from different scans or multiple campaigns. And we can also do change detection if we have time series of data. Now I will just like to show you how terrestrial laser scanning data looks like. Now this is not a photograph, but when we look at a zoomed portion, you will appreciate that this is not an image or photograph, but a point cloud of data for this feature. This is the Buddhist monastery, a Buddhist temple in Dehradun. So here you see this is a collection of very, very dense point clouds, and the very minute details in the railing, on the rooftop, and different parts of the monastery, staircase, etc. can be seen. So if very minute details are to be mapped, or very small features are to be mapped, etc., at higher level of detail, this would be very useful data. Now here if you see, this is again zoomed portion. So again I will emphasize that this entire thing is only a raw point cloud displayed here. You look at the statue, it appears that it is a photograph, but it is not a photograph, it is only a collection of laser point clouds. So range data only. So therefore you see any damage, etc., that may be there in course of time can be easily detected. And if details are to be mapped in 3 dimensions, this can also give us very high resolution information about that. So each small detail, every small carving, geometric design, etc., is all seen in great detail. Now, this is an example that was used for heritage documentation, built heritage, and damage assessment. So this is a church of the British era in the 19th century. So this is the photograph and this is the laser scan. Now, if you compare it, this is a shaded model, relief model. So here we don't have image, but we have only colored using the RGB information from the camera. This is the actual photograph. Now here the exterior was scanned from the outside, and the laser scanner was taken inside, and the interior was also scanned. Now with the help of this interior and exterior scans, we were able to get a measurement for the thickness of the walls, the interior structures, etc., right, the beam width, etc., and floor plans were generated. Now for heritage structures which are old, these kind of data, blueprints, etc., are not available. So creating such 3D blueprints is of great importance, so that in case of damage or some portion is lost due to some disaster, etc., then these can be used by the stakeholders who are into management and preservation, restoration of the heritage structures. Now here if you see another example of the raw point cloud taken from the laser scanner, you will appreciate this detailing with which the scan has been done. Even though the scanner was placed at quite some distance from the building, each small detail inside the building is also, this is a portion inside the building, scanner was placed outside, and the entire building is scanned along with the details of the interior. This here, if you look at this and if you look at the previous one, this has been colored using the RGB information, whereas this is only the point cloud and no coloring has been done with the RGB. Again, another panoramic view. This is another building. Again, to appreciate the kind of detailing that can be done, can be scanned. And this can be used for various kinds of applications. This is a building that is scanned. We can scan it for, we can use the scanner for other objects also. Now here, industrial applications. This is again some heritage related, so some statues, arches. These two are industrial related things. These are, the others are related to architectural, archaeological objects. So the kind of detail you can appreciate. We can also use it for mining activities to see how much of the amount of mining has been done. Is it done following regulations, or has the person mined more than he was given permission for, etc. So we can do a surface generation, and a two-time data collection will help us do the monitoring on a regular basis. So volume of the excavated area can be calculated. Uh, Laser scans can also be used for monitoring structural health of engineering structures like dams, bridges, and heritage monuments, of course. So this was one study that was done for heritage bridge condition assessment and 3D documentation of engineering structures. So the structure taken here was a bridge. Different types of bridges were covered, and along with TLS data. So this is a 3D model of the different kinds of bridges made with the help of a terrestrial laser scanner. Third kind of bridge. So structural health monitoring can be done. One can assess the condition based on whether there are some cracks developing, whether the crack is small or large, or is there some moisture related damage, some vegetation growth has been there, spalling is happening, etc. Then again, for these also, this documentation can be done by making blueprints of these structures. Here again, another example has been taken for documentation at different resolutions. So the data point cloud is taken from multiple scans. The 3D model, after co-registration of the multiple scans, the 3D model is generated, and then the point cloud is unrolled so that the entire assessment can be done. And after unrolling, it is resampled to different resolutions so that the user can decide based on the type of damage, whether it is a large crack or it's a small crack, or whether they need the entire data at very fine resolution, or they need to use only a small part of the laser scan at a medium to not so fine resolution. Then if we have pre-damage data and post-damage data, the breakage, etc., can be assessed based on the changes in the range information. So here there is a breakage, and the change in the depth amounts can be measured to see the damage. Here some cracks are there. So this is the pre-damage image where there is no crack. Here there is a crack. If we compare the two range data, then the depth of the crack can be estimated. In this railing, there is a breakage. So here we can see the amount of breakage, etc. And this, from the pre-damage area, we can use the measurements to do the reconstruction. Similarly, if cracks are detected by using, so here there is some damaged areas. Now in this, if we do using only the RGB data, that is only the image data, some portions which are not cracks but are coming out as edges and creating noise. So we only need to extract the crack area. Now, if the depth in data is included, then it eliminates the rest of the noise, most of the noise. That is because the depth can be measured by the laser scanner. That is, the laser beam will penetrate inside the crack, however small or large it will be, and give us a return based on the depth. So if we club the depth with the image data, we can do better classification and do crack detection or damage detection. Then if you integrate TLS and GPS and engineering drawings, so high resolution elevation information mapping etc. can be done. So this is done for the IIRS campus. Contours are generated. Different buildings are mapped. This is the scan of the building. Boundary walls for security purposes. Vegetation related studies can also be done. Right? Different buildings have been scanned. The 3D models are prepared. Industrial applications and mapping of these buildings, etc. have been done. So here you can see all the contours and elevation information is captured. Now it can be integrated in a GIS and query system, 3D model with database of infrastructure at floor level. So different floors, what are they, what are the usage of those floors, etc. Now to appreciate that even very small centimeter level objects can also be scanned. So you see here, this is a buried structure with different levels of pebbles and rocks, and at very high resolution this area has been mapped. The interior and exterior mapping, as we have discussed in the previous section also, for different structures, and then mapping can be done. Terrestrial lidar for, say, vegetation studies like biomass estimation, etc. So circumference at the breast height of the trees can be calculated. Tree heights, etc. can also be measured. Okay. So this is giving you a different, it is showing you the acquisition plan. So how the data set acquisition has been planned, what should be the plot size, how many scans, yeah, at 4 corners, 1 at the center, and so on. How it will cover the optimum region, right? What should be the settings, what is the vertical angle, what is the horizontal angle, at what angular resolutions the scan has been done, and so on. Now here it encounters different kinds of vegetation area. So tree extraction, different parts of the trees can be extracted, that is the stem, the branches, the thinner branches, and so on and so forth. Now if the tree is bending, then how it will calculate, and so on. Then disaster loss estimation. This can also be one application for high resolution 3D data collection. So the site here is very high slope and slum areas in the river, the stream beneath. So when there are heavy rainfall, water gushes into this stream, and due to heavy rainfall, some slope disengagement will also be there. So now if you see this, with this very high resolution map of the buildings and the slope areas, the debris flow can be generated. So at what speed will that flow come, and how many buildings will it affect, and so on and so forth. Similarly here, what will be the flow at different time periods, number of affected houses, and what is the population. So here a simulation based on the 3D mapping of that area. So as the water level increases, so the affected area, how many buildings, what is the population, etc. So this can be done at a larger regional level, larger level also. Then we can also use it for applications like landslide mapping. So this is the area of the landslide, this is the photograph, and this is where the laser scan has been done. So then the hillshade, aspect, slope map, etc. have been derived, and different derivatives, terrain derivatives have been calculated and assessed for different transects in the area of the landslide. This can be used as input for further analysis of the area of the landslide. Similarly, glaciers, etc., can also be monitored with this kind of study. So that this has given you a broad idea of what the applications, how to do scanning, do a project setup with the laser scanner, terrestrial laser scanner. What are the parameters of the scanner? What specifications you need to set before doing the scan, how to incorporate the GPS data into it, and the different application areas ranging from biomass estimation to archaeology to heritage to architecture, landslides, and many other civil engineering applications, and so on. So I hope you have had a fruitful learning session. Uh, Thank you very much. We will gather again for the question answer session in a little while.